Pain. Before we talk about how to stop it, you need to understand what it actually is. Pain isn't damage, pain is a signal, a message your nervous system sends to your brain to say something is wrong, pay attention, stop doing that. The damage happens in your tissue, the pain happens in your brain. And that distinction between where the injury is and where the pain is processed is exactly why different painkillers work in completely different ways. Your body has a pain detection system built from specialized nerve endings called nociceptors. They sit throughout your skin, muscles, joints, and organs, constantly monitoring for heat, pressure, chemicals, and damage. When they detect a threat, they fire an electrical signal up through the spinal cord and into the brain. The brain processes that signal, decides how serious it is, and generates the experience of pain. Notice the word generates. Your brain constructs pain. It doesn't simply receive it. This is why the same injury can produce wildly different pain experiences in different people or in the same person at different times. A soldier in combat may not feel a serious wound until after the battle. A person with anxiety may experience ordinary sensations as intensely painful. The signal is real, but the experience is built. Every painkiller in existence targets some part of this system. Some work at the site of injury, some work in the spinal cord, some work directly in the brain. And their differences aren't just chemical, they're architectural. They're attacking pain at completely different addresses. Here's each one. Ibuprofen. Ibuprofen is an NSAID, a non-steroidal anti-inflammatory drug. And the key word is inflammatory. When tissue is damaged, cells release chemicals called prostaglandins. These molecules do several things simultaneously. They sensitize nociceptors, making them fire more easily. They cause blood vessels to dilate, producing swelling. They raise the local temperature, producing heat. They amplify the pain signal before it even leaves the injury site. Ibuprofen works by blocking an enzyme called KIOX, cyclooxygenase, which is responsible for producing prostaglandins. Blocks COX, and prostaglandin production drops. Less sensitization, less swelling, less heat, less amplification of the pain signal before it reaches the brain. Ibuprofen doesn't touch the brain. It doesn't cross into the central nervous system in meaningful amounts. It works entirely at the periphery, at the site of injury, which is why it's effective for inflammatory pain like muscle soreness, joint pain, toothaches, and period cramps, but relatively ineffective for pain that doesn't have an inflammatory component. The trade-off is that prostaglandins do other jobs too. They protect the stomach lining, they help regulate kidney function, they support platelet activity and blood clotting. Block them across the whole body, and you can get stomach irritation, kidney stress, and increased bleeding risk. The drug doesn't know which prostaglandins you wanted it to target. Aspirin. Aspirin works through the same COX blocking mechanism as ibuprofen, but with one critical difference. Ibuprofen's blockade is reversible. Aspirin's is permanent. Aspirin chemically modifies the COX enzyme so it can never recover. The cell has to build an entirely new enzyme from scratch to replace it. For platelets, which have no nucleus and can't synthesize new proteins, this means a single dose of aspirin disables their clotting function for the rest of their lifespan, roughly 7 to 10 days. This is why aspirin is used in low doses for cardiovascular protection, thin the blood, reduce clot formation, protect against heart attacks and strokes. But it's also why aspirin requires more caution than ibuprofen around bleeding risk, surgery, and certain populations. For pain, aspirin and ibuprofen are broadly similar in mechanism. Aspirin simply commits harder. Paracetamol. Paracetamol, known as acetaminophen in North America, is one of the most widely used drugs in the world and one of the least understood. Scientists know it works. They're still debating exactly how. The leading theories suggest paracetamol works centrally, meaning inside the brain and spinal cord rather than at the injury site. It may inhibit a COX variant found primarily in the central nervous system. It may modulate the endocannabinoid system, the same network that cannabis interacts with. It may enhance descending pain inhibition, the brain's own system for dampening pain signals coming up from the body. What's clear is what it doesn't do. It has almost no anti-inflammatory effect. It doesn't reduce swelling. It doesn't sensitize or desensitize nociceptors at the injury site. It works on pain perception rather than pain production, which is why it's effective for headaches and fever, but less effective for inflammatory conditions like arthritis. The critical issue with paracetamol is its safety window. At therapeutic doses, it's exceptionally safe, but the gap between a therapeutic dose and a toxic dose is narrower than most people realize. The liver metabolizes paracetamol into a toxic byproduct called NAPQI. At normal doses, the liver neutralizes NAPQI easily. At high doses, or with alcohol consumption, which depletes the neutralizing agent, NAPQI accumulates and destroys liver cells. Paracetamol overdose is one of the leading causes of acute liver failure in the developed world, not because it's dangerous when used correctly, because it feels so safe that people don't treat it with appropriate caution. Codeine. Codeine is where painkillers make their most significant transition, from drugs that modify the pain signal to drugs that speak the brain's own language. Codeine is an opioid, a naturally occurring one derived from the opium poppy. When you swallow it, the liver converts approximately 10% of it into morphine. That morphine then binds to opioid receptors throughout the brain and spinal cord, the same receptors your body uses to process its own natural painkillers, endorphins, and enkephalins. When opioid receptors activate in the spinal cord, they block the transmission of pain signals climbing toward the brain. When they activate in the brain itself, they alter how pain is perceived and how much it matters. Pain may still be detected, but its emotional weight, the suffering component, is dramatically reduced. This is the profound difference between opioids and peripheral painkillers. Ibuprofen reduces the signal. Opioids change the response to the signal. A person on opioids may acknowledge that something hurts while being entirely unbothered by it. Codeine is considered a weak opioid. Its potency is limited by how much morphine the liver converts it into, which varies significantly between individuals based on genetics. Some people convert very little and experience almost no pain relief. Others convert so efficiently that a standard dose delivers a morphine-level effect. Tramadol. Tramadol is a synthetic opioid with a dual mechanism that makes it unusually complex. Like codeine, it binds to opioid receptors, but it also inhibits the reuptake of serotonin and norepinephrine, the same mechanism used by certain antidepressants. These neurotransmitters play a role in the brain's descending pain modulation system, the pathway that sends signals down from the brain to the spinal cord to suppress incoming pain. So tramadol attacks pain from two directions simultaneously. Opioid receptor activation blunts the pain signal. Serotonin and norepinephrine reuptake inhibition strengthens the brain's own pain-suppressing system. This dual mechanism also produces its dual risk profile. Tramadol carries opioid addiction potential and opioid overdose risk, but its interaction with serotonin also creates the possibility of serotonin syndrome, a potentially dangerous condition caused by excess serotonergic activity, particularly when combined with antidepressants or other serotonergic drugs. Tramadol is stronger than codeine, less potent than morphine, and more complicated than either. Morphine. Morphine is the standard against which all other opioids are measured. It binds powerfully and directly to opioid receptors throughout the central nervous system without needing conversion by the liver. Its effect is comprehensive. Pain signals are blocked in the spinal cord. Pain perception is altered in the brain. The emotional response to pain, the suffering, the dread, the urgency, is dramatically suppressed, and the brain's reward system is simultaneously activated, producing the warmth and euphoria that makes morphine both medically invaluable and dangerously addictive. Morphine's power is also its problem. Tolerance develops quickly. The brain downregulates its opioid receptors in response to persistent activation, meaning you need more morphine to achieve the same effect over time. Dependence follows. Withdrawal, when morphine is stopped, is brutally physical. Every system the drug was suppressing rebounds at once. Respiratory depression is morphine's most serious acute risk. Opioid receptors in the brainstem regulate breathing. activate too many of them too strongly, and the drive to breathe diminishes. This is the mechanism behind opioid overdose death. The brain simply stops signaling the lungs to inhale. Local anesthetics. Local anesthetics, lidocaine, novocaine, bupivacaine, work through a completely different architecture than anything discussed so far. They don't modify pain signals. They don't interact with receptors. They physically block the electrical conduction of nerve cells entirely. Neurons fire by allowing sodium ions to rush through channels in their membrane, creating an electrical impulse. Local anesthetics bind directly to those sodium channels and hold them closed. No sodium flow, no electrical impulse, no signal of any kind, pain or otherwise. The nerve becomes completely silent. This is why dental anesthesia numbs not just pain, but all sensation and movement in the affected area. The nerve isn't sending modified signals. It isn't sending any signals at all. Local anesthetics wear off as the drug diffuses away from the nerve and is absorbed into the bloodstream. The sodium channels reopen. Sensation gradually returns, usually in the distinctive pins and needles pattern of a nerve waking back up. Every painkiller in this list is targeting the same outcome, less pain, but they're arriving at that outcome through completely different mechanisms, at completely different points in the pain pathway, with completely different risk profiles and trade-offs. Ibuprofen quiets the signal at the source. Paracetamol alters perception centrally. Opioids speak directly to the brain's own pain language. Local anesthetics silence the nerve entirely. Pain is a message. Painkillers are different ways of interrupting it. Understanding which interruption you need and at what cost is the difference between treating pain and just masking it. If you've enjoyed this video and want to see more, please comment, like, and subscribe. Let's keep growing together.